Hi, and welcome to our presentation on the Optical Resistor Scanner Identifier. I'm Raynard, and my team members are Matthew and Daniel. Our client is Stephen Knudsen, and our technical advisor is Dong-Hun Xu. So our project is an optical resistor scanner identifier, which is based on a Raspberry Pi and is our way of promoting the reuse of resistors within the ECE department. To achieve this, we decided to utilize a machine learning model that detects the resistors in tandem with image processing to determine the wattage and the value of the resistor. A user will start a session on the optical resistor scanner identifier and will scan the resistors. Scanned resistors are then uploaded to our database and then immediately available to be seen via our web application. Overall, we were able to meet our minimum walking skeleton requirements. However, we did run into a few key issues that prevented us from progressing further. We were able to get resistor detection working, integrate the database with the application on the Raspberry Pi, as well as developing, deploying, and integrating the database into our web application. However, we ran into issues where it came to color detection. We chose a camera to reduce the cost as per our client's request, but the camera's image quality was too poor to be able to accurately detect band colors on the resistor. Because of this, we ended up switching cameras to a more expensive, better quality one in order to continue with the development of our color detection algorithm. We also had issues with creating a smooth UI due to processing power limitations of the Raspberry Pi. Due to time limitations, we were not able to further improve upon object detection to limit the amount of false positives. We were also not able to further improve upon the color detection algorithm for false positives as well, leading to incorrect detection of resistor values. We will now move on to a demo.
This is the demo for the optical resistor scanner identifier, and what we have here is a 7-inch touch display with a Raspberry Pi camera looking down on a white scanning area. We also have an LED lamp connected via USB to provide consistent lighting. In this demo, we will scan a single resistor by placing it on the scanning area. And as you can see, the resistor is being detected, as indicated by the blue bounding box. Now, implementing color detection on the Pi camera proved challenging, so we opted to use a better camera. In this setup, we've replaced the Pi camera with one that has a higher resolution and better color range. I'll place a 4-band resistor on the scanning area. And from left to right, we have red, yellow, brown, and gold. For this combination, we have ourselves a 240 ohm resistor. The scanner also identifies the power rating as 1/8 watts. Now the scanner also works for multiple resistors. Here we have 4 resistors of the same value, and 3 red bands gives us 2200 ohms. The power rating for these resistors is 1/4 watts. Note that the scanner doesn't take into account the gold tolerance bands. This is because tolerance bands are more reflective compared to the colored bands, making them harder to detect. The scanner comes with a database that keeps a record of all scanned resistors. To begin a scan session, we hit Start on the top left corner, and then we hit Scan to send resistor information to the database. Then we hit End to conclude a scan session. The database records are viewable in a web application, which we will present next.
This is the front end of our optical resistor scanner identifier and is where all the data collected from the scanner can be viewed. The website allows students to view the inventory of scanned resistors anywhere at any time. It is connected to our database and listens in real time for any new data being uploaded. Students can use the database to view past sessions like this one from Friday, April 1, 2022, and see the resistors that were scanned on that session. They can also look at other sessions like this one from Sunday, April 3rd, and we can see that 8 resistors were scanned during the session. We can see that each resistor has a resistance, its wattage, and the exact time and date it was scanned during this session. Sessions can also be viewed in real time. For example, we can see that a new session was just added. There are currently no resistors, but soon enough, more resistors will be coming through as they are scanned. As we can see, a new 200 ohm resistor was scanned with 1/4 wattage. As more and more resistors are scanned during this session, the information is automatically updated without having the user refresh the web page.
Thanks for those demos, Raynard and Daniel. My name is Matthew, and I'm going to be going over some of our thoughts on how this project went for us over the past semester. First off, I'll start with an overview of our intended design that we set out to work towards at the beginning of the project. As described in our project proposal, we wanted to design a reliable system to scan and store resistor values from used resistors of old lab kits to aid in sorting and storage and for ease of future use for students working on various projects. The prototype was built using a Raspberry Pi microcomputer, a 7-inch LCD touchscreen display, and a Raspberry Pi camera. Object detection for detecting resistors in the view of the camera was implemented using a Haar cascade machine learning algorithm, and the resistor band detection was done by detecting contours in the image in the area where a resistor was identified and determining pixel values inside of these contours using a mask over the image. Wattages of resistors are determined by measuring the length of the resistor, as the scanning area always remains a fixed distance from the camera. After scanning, resistor values in wattages are stored in a remote database and are viewable from a custom website separated into sessions of resistor scans defined by the users of the scanner. Now, I'll go into a bit of detail about what parts of our project went well for us during development. Firstly, the object detection algorithm works quite well, and after retraining the machine learning model a couple of times, it results in very few false positives and almost no false negatives when using the Raspberry Pi camera. Secondly, the web application and database integration was implemented very early on in the project and has had very few problems throughout the process of our project work. Lastly, our algorithm to determine the wattage of a detector resistor has worked reliably since its implementation, as it is a fairly straightforward method for doing so. Now for what didn't work so well in our project. As we neared our deadlines, color detection was still proving to be a major problem halting our progress. Simply put, the Raspberry Pi camera we were using did not have a good enough resolution, nor was its color saturation sufficient to differentiate between different color bands on the resistors. For example, yellow bands on the resistors are nearly impossible to distinguish from the rest of the resistor body for beige-bodied resistors in the camera view. As shown previously in our demo, using a higher resolution camera allowed our color band detection algorithm to work much more reliably than we could achieve using the Pi camera. Due to delays caused by our struggles with the color detection, we were not able to properly implement or verify the functionality of the color detection for blue-bodied resistors. However, our object detection does work as reliably for blue bodies as it does for beige. Another smaller problem we ran into was that the processing power of the Raspberry Pi itself often struggled to keep up with running our detection algorithm as often as we wanted to, resulting in low frame rates and multiple second delays between changes in the reality of the scanning area and what was actually appearing on the screen. Now to talk about where this project could be taken next if we or another person or team were to continue working off of our design. The first obvious step would be to commit to using a higher quality camera and improving the color detection algorithm to be more reliable for beige-bodied resistors, as well as verifying that it functions for blue-bodied resistors, and if it doesn't, then implementing functionality for blue-bodied resistors as well. Another improvement that could be made is increasing functionality of the web application, such as allowing site visitors to sort the resistors based on value and or wattage, in cases where someone is checking to see if there are specific types of resistors available for use in the labs. Lastly, we can further improve our object detection model to remove the occasional false positives and negatives that arise with our current model. Overall, our design was relatively sound on the software side of things, but was held back by a poor choice of hardware components. We had an option at a certain point of changing to a cheaper Adafruit display, which may have allowed us to acquire a better camera without impacting our budget too much. However, at that time, we were still under the impression that implementing the color detection on the components we were currently using would be feasible. If we could go back and start attempting to implement our color detection algorithms earlier on in the project, we likely would have had more time to make changes in our selected components and come out with a more satisfactory prototype in the end. Our machine learning object detection was an interesting challenge, as none of us had had very much experience with the technology beforehand, and while time-consuming, it was very satisfying once it was working. Thank you for listening to our presentation, and we would now like to open the floor to any questions you may have.